Welcome to this Starter Scope video tutorial featuring shaft systems. In this session, we'll guide you through the modeling and simulation of a two-stage reduction gearbox using the tools provided by the MESYS Shaft System module. You'll learn how to define shafts with a focus on strength aspects, create shaft groups, position these shafts, define and pair the relevant gears based on connection rules, apply loads, and evaluate the system under realistic operating conditions. Now, let's take a look at the functional principle and power flow of this gearbox based on its technical drawings. This gearbox consists of three parallel shafts: input, intermediate, and output shaft. Power enters via the input shaft and is transmitted through two gear stages to the output shaft. Direction of torque flow and shaft speeds are defined by the gear pairing and the geometry. For evaluation purposes, we consider a typical operating condition with a torque of 630 Nm and an input speed of 385 rpm, representing a relevant load case. In settings, gears can be treated not only as stiffness, but also with mass and geometry via increased shaft diameter. The required life is passed to the gear calculation connected to the system and is also used in the shaft strength calculation. For the latter, infinite life should be selected and shear deformations are evaluated using the Hutchinson approach. As lubricant, let's select a synthetic ISO VG 460 and a contamination of this level. For detailed options under display settings, please refer to the software manual. For systems with shafts that are not coaxial, shaft groups have to be added. To model a gearbox with parallel shafts, we start by creating three separate shaft groups with their individual shafts. Once the groups are defined, we move on to build the shaft geometry. This can be done using the classic matrix input or by importing geometry from a STEP or DXF file, depending on your workflow. Make sure that all three shafts are assigned a material with parameters suitable for strength verification according to DIN 743. In the meantime, all three shafts have been defined geometrically. You can check and verify the shaft dimensions by hovering the mouse over the respective shaft segments. Once all geometry data is confirmed, we proceed with applying the system loads under the Loading tab. Click the plus button and select Coupling from the drop-down on the right. Assign a suitable name and enter the input torque and speed accordingly. Then, still under the Loading tab, use the plus button again to insert a cylindrical gear. Assign the name and fundamental parameters according to the gearbox specifications. Optionally, a gear body can be defined for external gears by specifying its actual position and diameter. It adapts automatically to gear data, but is only considered if 3D model is enabled. To complete this step, assign the corresponding loads and gear elements to the remaining shafts as well. Let's now define the supports. Select shaft 1 in the system tree, go to the Support tab, click the plus button and choose Rolling Bearing from the drop-down. Name the bearing and position it using the blue arrows to move it to the adjacent shoulder. Shift and left click to move it freely or by entering a value directly in the axial position field. Open the bearing module by clicking the plus button in the lower right corner or by selecting the bearing name in the system tree. Besides defining custom inner geometry, outer geometries or ratings, you can also filter the database for generic or manufacturer-specific bearings. Assign the bearings on the input shaft. Make sure to assign a standard normal clearance class to all bearings. And configure the right-hand side as a floating bearing. Repeat this process for the remaining shafts. Continue now by selecting shaft 3, adding another support and choosing coupling for a reaction torque from the drop-down. This element fixes the shaft's rotation angle and is used to take the torque zoom. In the Sections tab, you can define multiple cross-sections along the shaft, each relevant for strength verification according to DIN 743. These sections are typically placed at geometric transitions, such as shoulder steps, keyways, grooves, or undercuts, where stress concentrations may occur. Notch details like fillet radius, notch depth, and geometry type can be specified directly for each section. As we have already configured the strength calculation settings on the shaft system, let's now go ahead and assign the relevant notches across all 3 shafts. Now is the right moment to assign and mesh the gear pairs. In MESYS, this is done by selecting gear connections in the system tree. Each pair is defined by assigning the respective input and output gears, one at a time. This sets up the kinematic link and enables calculation of load transfer, gear forces, and shaft reactions. Activate both gear pairs and assign them via gear connections. Shaft and gear data are shown, and gear parameters can be edited jointly or individually. Select colors for each pair and leave the remaining gear-specific settings unchanged for the scope of this tutorial. At this point, all shaft groups still share the same coordinate origin, as visible in the Group tab located in the lower right corner of the interface. To align the gear pairs physically, the shaft groups now need to be positioned relative to Group 1, based on the gear connections. Open the positioning window via the system tree. Positioning can be carried out using various criteria, typically based on the spatial relationship between gear pairs or shaft groups. Use the plus button on the right to add 2 constraints and define them for Group 2 and Group 3. Set their relative alignment along the horizontal Z direction. As a result, the shaft groups are now correctly positioned in space. This positioning can also be reviewed via the positioning window, gear connections, or shaft dialog, all accessible through the system tree. For a numerical view, you can select each group in the system tree and open again the Group tab in the lower right panel of the interface. All required inputs are now defined. It's time to launch the calculation. Start it via the calculation menu, the ribbon icon, or simply by pressing F5. A green checkmark in the bottom right corner confirms that the model is consistent. The results overview provides key outputs and can be customized under Extras, Results, Overview. Use the graphics menu to view the 3D geometry, including the power flow in the XZ plane. The deformed 3D graphics give you an idea of where the system is most affected on the load. The Shafts tab shows global shaft results. The Sections table lists all cross-sections with notch types, DIN 743 safety factors, forces, and displacements. The Bearings table summarizes bearing life, loads, contact pressure, misalignment, and more, configurable via right-click. The required H-life is not achieved for the deep groove ball bearing on the input shaft and the 2 cylindrical roller bearings on the intermediate and output shaft. Since sufficient space is assumed, we replace them with a larger bearing series to meet the modified reference life. The moment has come to evaluate the gear connection behavior and see whether any improvements are needed. Let's begin by simplifying the center distances to practical manufacturing values. Next, we'll use the profile shift graphics, specific sliding and safety factors over profile shift, to get an initial impression of gear performance. Profile shift refers to the intentional displacement of the generating tool during manufacturing. A positive shift increases tooth thickness at the reference diameter and allows for targeted optimization of specific sliding and root strength. Although ISO 6336 does not specify exact limits for specific sliding, it reflects its influence indirectly through correction factors, for example, those related to strength and wear resistance. Under the gear connection window, we can open the Define Profile Shift dialog. Let's apply the proposed values based on balanced sliding for both gear pairs. Then launch the calculation and observe updated graphics. Let's now take a closer look at tooth flank modifications, a key step in optimizing gear contact under load. To evaluate their effectiveness, we activate three key diagrams. The line load plot shows how forces are distributed along the tooth width. The gap width diagram reveals local separations under operating conditions, and the tooth flank modification view, which displays the resulting modification geometry. In the Gear Connections dialog, the Tooth Flank Modifications tab allows you to define crowning, line slope, or end relief along the tooth width. These targeted modifications help improve load distribution and reduce edge contact, particularly in helical gears. Reliefs are defined over the active flank width and can be applied to one or both sides of the tooth. These visualizations support the assessment of whether the applied flank reliefs lead to smoother contact, reduces stress peaks, and improved gear performance. Whether these values are ultimately feasible or reasonable from a manufacturing perspective is beyond the scope of this analysis. Please note a helpful time saver in the status bar. This small button next to the calculation symbol allows toggling between M and A. M means that calculations must be triggered as usual. Meanwhile, if set to A, calculations are executed automatically after each input. Naturally, this mode should be avoided for models with longer computation times. The results can be reviewed either in detail via the shafts, sections, and bearings tabs on the right, or in filtered form via the results overview at the bottom of the user interface. The report menu allows immediate generation of a full or partial report, and the results tables can be exported to Excel. As usual in MESYS, always just a few clicks away. At this point, we'd like to thank you for your attention. Hopefully, this tutorial has given you a solid impression of the value MESYS can offer, and we look forward to welcoming you again in a future session.